Thanks very much, Austin. I'm really glad to be here. I also owe Austin an apology because he's heard this talk something like 3 times in 4 months, but at least some of the rest of you haven't yet. Right, so what this talk is about is a way of preparing interesting, highly entangled quantum states that's maybe a bit different from the ones that you most often hear about. So as you know, Hilbert space is a large and scary place, and most points in it are very far from anywhere else. But most of Hilbert space is not just very complicated, but it's also fairly useless. So the states that are actually good for any potential purpose you might conceivably have are very sparse, and most of these states have relatively efficient recipes for constructing them. Now, the most familiar such recipe is the recipe for varying a ground state, which is you start with either cool the system down to its ground state, or, for example, you start the reference state and change your parameters really, really slowly. So by the adiabatic theorem, you track along to the ground state of the Hamiltonian you really care about. Now, can you still hear me? Okay. Right. Adiabatic preparation is efficient when you're in the right phase, but when you're trying to create critical states, gapless states, things like that, it's necessarily an inefficient and slow process. And so there's been a quest for other ways of constructing states, and so an approach that's really in vogue nowadays that I won't have very much to say about is to try and get to a ground state using things like dissipation or measurements and feedback. What I'm going to talk about is something that has some similarity with this idea of preparing states using dissipation. It's going to be a peculiar type of dissipation, and so I'm going to prepare states by having a machine that spits out 1 qubit at a time, and when you've collected all the qubits, those qubits are guaranteed to be in the highly entangled state you are trying to get at. Okay. So to explain what this protocol is about, let me just remind you very quickly about a few sort of elementary properties of open quantum systems. So what an open quantum system is it's the universe. The universe undergoes closed unitary evolution, and you might declare by fiat that you only care about some parts of the universe, and you want to ignore other parts of the universe, and so you by fiat declare that these guys your system. And those guys, your environment, and you want to have some kind of description that describes the system and not the environment. Okay, so this is too general because this is just a description of some very general quantum evolution. So this is so general as to be intractable. And to make some more progress, what people often do is they write down a simplified model of what the environment is. And the most natural simplified model is that of a Markovian open system. So in a Markovian open system, what happens is that at each time step, Bob comes in with a new qubit or a new qubit or some new Hilbert space that's in a reference state, which I've marked by this little blob. By the way, most of you, I assume, were at Austin's talk this morning, so this notation should make sense. So the vertical lines are Hilbert spaces. There might be qubits. They might be something more complicated. The blobs, the blocks here are unitary gates, and this little red blob just says that I'm starting these qubits of Bobs out in some reference state, which I might as well call 0. Okay. So at each time step, Bob comes in with a 0. And then Bob interacts with Alice via some kind of unitary, and then Bob's qubit wanders off and is never seen again. Next time step, Bob brings in a fresh qubit, and that's why this evolution is Markovian, because Bob's part of the system has no memory. Okay, and so I can try and simplify the notation a little more by getting rid of Alice's internal dynamics and folding it into describing Alice's system via fattened legs, various things going on along the fattened leg, but they happen in the analysis system. So this is my schematic description of a general Markovian quantum system. And this is a description of the full universe. Okay. By the way, please do interrupt me if you have questions, because this bits of this talk build on each other, and it's better to get questions out of the way when they're actually relevant. Okay. Okay. So this is how the full universe evolves under Markovian open system dynamics. Now, the normal perspective that you take is to trace out Bob's degrees of freedom, because Bob's qubits have gone away. You say, okay, you have no access to them anymore, so you have to, you've got to trace over them, and that gives you this kind of superoperator evolution, which you can call a quantum channel, and which many of you probably know better as a Lindblad-Messer equation. Now, instead of tracing out Bob's degrees of freedom, you could also take the perspective that that Bob performs a measurement on his qubit after it's come out, and that measurement outcome defines a quantum trajectory, which, for example, is the kind of thing that Sarah Fazio was talking about yesterday. And if you average over trajectories with the appropriate weights, you get back the quantum channel. In a sense, the relationship between these two things is you break this leg by introducing a complete set of states. Okay. The perspective I want to take in this talk is different again, and it's the following. It's that Alice starts out in a reference state, and then Bob keeps coming in at each time step with reference state qubits, and they wander off, but they don't wander off, you know, and disappear. Bob collects them and keeps them in a safe. And at the end of the process, Bob has collected a bunch of qubits. And then when this has gone on long enough, we're all bored. Alice performs a final rank 1 measurement on her state, and so as you can see at the end of that, Alice has no legs anymore, and so this state is entirely a tensor living in Bob's Hilbert space, and so I'm going to ask what the properties of this tensor are. That's where we're going. Yeah. Bob, let me come back to that. Right now, Bob needn't make any measurements. So in practice, if you wanted to think about what this looks like, you know, there's an emitter and it keeps emitting radiation, and Bob collects the radiation. And you know, what does Bob do with it? Well, Bob could perform measurements on it, but doesn't have to. Bob could instead just hang on to his qubits by sort of sending them round and round a delay line until he's collected all of them. So he hasn't looked at them because he's sort of still circulating in a delay line. Alternatively, once I've told you how all this works, you can just reinterpret it as a quantum circuit with some kind of funny sequential geometry. Okay. I am, because at each step, I mean, Markovianity is just the fact that Bob at each time step comes in with a qubit in the reference state 0, and that doesn't depend on anything else. So that's Markovianity. But I'm taking this, that's what I call Markovian dynamics. But yeah, it's a flip Markovianity, because now, you know, it's Markovian in some sense from Alice's perspective, but I've sort of flipped my perspective and now I'm Bob. So it's no longer really Markovian because from Bob's perspective, Alice contains a memory. Okay. Right. Yeah, great. So do keep asking questions. Anyway, so that's the logic of doing this. But for most of the rest of this talk, I'm just going to say this is what we care about, this kind of object. And I want to ask what the properties of this kind of object are. Now, this isn't an entirely new question, because if you take what I had in the previous slide and you flip it sideways and you trim out all these zeros, because you know these zeros aren't really doing anything in the tensor network, right? Because there's no free indices attached to them, so you might as well clean them up and get rid of them. Once you've done that, what you have is something that many of you would recognize as a fairly standard diagram of a matrix product state. And in fact, it's well known that, and it's been known since Sarang's work about 15 years ago, that this kind of process of taking a Markovian dynamics and reading it backwards generates a matrix product state whenever the Hilbert space on this black thick leg is a finite dimensional Hilbert space, and the complexity of the MPS that's generated is set by essentially the size of the Hilbert space that Alice has access to. Okay, and so when in the case where you take the thermodynamic limit while keeping Alice's system size fixed, we have an MPS of finite bond dimension. And what I want to ask about in this talk is what happens when you don't make that assumption, when you allow yourself to talk about things, when you allow yourself to talk about the radiation from systems that are more complicated than just finite dimensional Hilbert spaces. Why would you do that? Well, because matrix product states at finite bond dimension are, if you like, they're not expressive enough to talk about critical states or phase transitions or many of the things that a condensed matter physicist would care about. And so one would like to have a family of radiated states that's expressive enough to actually ask these questions for and maybe address them. Okay, so that's where we're going. And so the two payoffs from this, I would say. So the first is that what we're doing, the recipe I'm going to discuss is as follows. You start out with a familiar open system dynamics, then you break it up. So you talk about it as a dynamics in expanded space consisting of Alice and Bob, and then you flip your perspective, and then it's a state that lives only in Bob's degrees of freedom. And the upshot of all of this is that you start out with something that's pretty simple, which is just dissipative quantum systems, stochastic processes, master equations, like nice friendly stuff. But then you turn this crank, and first of all, you get interesting many body states that you might not have thought about otherwise. And secondly, it might allow you to generate certain highly entangled many body states much faster than any other known recipe. So those are the two potential payoffs, and I'm going to hopefully get to explaining how those do actually cash out. Okay, so before I do that, let me just say one technical thing, because it connects to something in Austin's talk this morning, which is if you want to talk about if you want to compute an entanglement property of an MPS, what you would do is you would compute, for example, the trace of the square of a subsystem density matrix. And if you're used to these manipulations, you'll see that what that is so over here I've traced out the complement. There's two copies because I have rho squared, and then over here what I'm doing is matrix multiplication. Okay, and so this entire tensor network diagram represents the entanglement of this radiated state. Now, if the states, and so the key point is that if you want to evaluate this, you'll notice that this motif that I've boxed appears over and over again. But this motif, if you think back a few slides, is just the quantum channel. So if you know how to implement the quantum channel, you know more or less for free how to contract this entire object sideways. So you zip in from this side using the Heisenberg picture channel. You zip up from that side using the Schrödinger picture channel. And when the dust settles, what you end up with is this very simple expression for the purity of the state that relies only on properties of Alice's Hilbert space, which the conventional notation is to call that the bond space. And in the case of an MPS, where the memory time is finite and you take your system size to infinity, any operator eventually turns into the identity, and any initial density matrix becomes a steady state density matrix. And so you get this result that the entanglement properties of the MPS are precisely the steady state. The entanglement entropies of the MPS are precisely the entropies of the steady state density matrix of the corresponding quantum channel. Which kind of makes sense, because the steady state density matrix sort of keeps track of how much information is being stored in the bond space. Okay. And so, right, so this construction tells you if you want to construct a highly entangled state this way, you need the steady state density matrix to be something with a lot of entropy. Okay. And so just a slightly more intuitive way of seeing what's happening here. So if you think about this simple state, which is just a bunch of bell pairs that I've sort of scattered about at random. So the lines tell you which pairs of qubits are in bell pairs. And so, you know, across a cut like this, you have 3 bits of entanglement, right? Because you cut 3 bell pairs to create that. If you think about this, if you think about how you generate this sequentially, well, it's fairly obvious, right? So you create a bell pair, send 1/2 of it out to Bob at time 0. Alice hangs on to the other half of it until it's time to release the other half of the bell pair. At that point, Alice emits the qubit that she's been holding on to. And so the entanglement of the state is related to the number of halves of bell pairs that Alice had to hold on to in order to generate the state with the qubits in the correct order. Okay, so if you like, this is sort of the bond space is a kind of memory for the okay. So if that's, let me stop here and ask if there are any questions at this stage before I go on. Yeah. So far I've been very general, so I've made no assumptions about that, but in what I'm going to talk about next, it will be local. Yeah, that's right. But yeah, so far I've just been sort of presenting the overall formalism. Anything else? Okay. Yeah, go ahead, Amos. Yeah, what I've been saying is very much like the black hole information problem, right? Except the black hole is the case. It's related to a situation where the bond space is really just a giant, you know, is just subject to giant random unitary. And I'm going to talk about things that are much more structured. So not quite black holes. They're radiating. Just because it radiates doesn't mean it's a black hole. Yeah. No, I'm very specifically restricting to Markovian dynamics. So to the extent that there's any non-locality in Bob's side, it comes from the fact that Alice is storing information in her bond space. Okay, so it is the case that if you have a Markovian open system, it can have long-range correlations in time, right? Because those are properties of the open system dynamics, not properties of the setup of the problem. But yeah, that kind of non-locality exists, nothing else. Yeah. Yes. Yeah, yeah. Yeah. There's some amount of philosophical resemblance there, but the big difference is that the central spin model is not sequential. So in the central spin model, all the peripheral spins are always talking to central spin, whereas here, the talking is in sequence. Okay. Yeah, I would think so, because the central spin model, you don't quite have the same strong notions of locality that I'm going to get out of this, right? Because for me, the spatial locality of the MPS is related to the temporal locality of the Markov chain. Yes. Yeah, no, that's right. That's a great question. I think it leads to yet another family of interesting phenomena, but I don't have anything to say. I don't have anything concrete to say about that yet. That's sort of work in insufficient amounts of progress to talk about. Okay, so now let me give you some examples of what comes out of this perspective. And so the first. So again, the program here is to take a stochastic process and then turn this crank. And after you're done turning this crank, you end up with an interesting quantum state. Okay. And so I'm going to begin with basically the simplest stochastic process I can think about that has a phase transition. And that's the following. So I have a particle on a half line with a reflecting boundary at the left end. And so the particle can hop right or left. When it hits the origin, gets reflected. And so in general, the rates to hop left and right are different. And so this model has three phases. So it's got a phase where the left hopping dominates and the particle is more or less stuck near the origin. It's got a phase where the right hopping dominates, the particle just drifts off to infinity. And between those, it's got a critical point where you're effectively just undergoing a random walk. Okay, and so now this is my stochastic process, and so the crank I want to turn is I want to first, okay, so I don't need to really write down. So this step is a bit trivial, but all I'm doing is I'm taking the stochastic process, which is a classical stochastic process, and saying I can promote it to quantum channel by just saying it leaves populations that's diagonal elements of density matrix alone and doesn't do anything interesting mixing the diagonal and the off-diagonal elements of density matrix. Okay, and so now I can take this thing that I've promoted into a quantum channel, and I can perform a dilation of the quantum channel in terms of not qubits, but q-trits on Bob's side. So Bob's objects are now spin 1 rather than spin 1/2, but that's not important. Okay, so the perspective now is that Alice has a Hilbert space with a bunch of sites labeled by the position of this one particle on the half line, and then when Bob and Alice interact, Bob comes into 0, and Alice either moves left and releases a 1 to Bob, or moves right and releases a -1 to Bob, or does nothing and releases nothing to Bob. So what happens with this process is that the change in Alice's state is written into Bob's system. So so once you've done this dynamics a bunch of times, it's easy to convince yourself that that where you end up is that with some appropriate weights, depending on the left and right hopping rates, you end up with a superposition of histories like this, where Alice's state at the end of the history is just the end state of the history, but then the history of moves that led to that end state is written into Bob's system. And when you measure Alice's final state, then you perform a projection on this guy, and then once you perform that projection, then you're just left with a superposition of all histories. Bob's state is just superposition of all histories with that starting point and that end point. And if you don't like some of the endpoints, you can post-select them out, and then that gives you the fixed boundary conditions that you wanted for your state, at the cost of some post-selection overhead, which we would like not to be too large, but that is ultimately what determines how efficient or not this process is. Okay, so that's what we have. And so in this simple example, yeah, go ahead. Yeah. Yeah, you're just keeping them. Yeah. Yeah, you have a density matrix in Alice. And so density matrix really is just a weighted superposition over all the end states you could end up with. And that's precisely the probability distribution of the random walk. Yeah, though it's a bit subtle to think about it as trajectory, but yeah, you could do something like, you could think about it like that. But yeah, it's really best to think about this as like some state on the universe, and that state in the universe is just like you're collecting terms. So each end state comes with a collection of terms associated with it that are all the histories that could have led to that end state. Okay, so right. Anyway, so what is the state you get out of this for the random walk? It turns out this is a familiar state called the Motzkin state, which is a well-known critical state that was discovered by Peter Shor about 10 years ago. And so the idea is, okay, so I think I said most of this already, Yeah, so yeah, let me actually, sorry, let me just say this, so I'm making sense. So, okay, so this is what you end up with, okay? And now there are two questions to ask. The first is, you know, suppose I insist on Alice's end state being the 0 state where she started out. So that's at the origin. That's just something to pick. So I'm going to choose it. Okay. So if that's my choice of end state, then you know, how much post-selection overhead do I have to pay? How many times do I have to throw out the run because I ended up the wrong end state? That depends on which phase you're in. If you're in the phase where you're stuck to the wall, then there's basically no post-selection overhead because you're never really moving far from the wall anyway. So there's order 1 post-selection overhead. If, on the other hand, you're in the phase where you're drifting away, then you're exceedingly unlikely to end up back at the origin, and the post-selection overhead is ginormous, and this would not be an efficient way of constructing the state. If you're somewhere in between, if you're at the critical point, then the post-selection overhead is, you know, the longer you run the process, the lower this probability is, but it only goes down as like 1 over square root of time, which is 1 over square root of the size of the state you're creating. So it's some post-selection overhead, but it's only polynomial. Okay, and so the claim is that this also determines, you know, the width of this distribution also determines the entanglement of the state that's generated in Bob's qubits, and in particular, in the phase where you're stuck to the left, you're exploring a finite fraction of this line, and therefore your entanglement goes as an area law because your bond dimension remains finite. At the critical point, you spread out over, after running this process for a time t, you spread out over a distance square root of t, and so your entanglement, you would predict, goes as 1/2 log t. And in this phase, well, we don't really care about that phase, so I'm not going to talk about it. So yeah, so indeed, this checks out. So if you're in the phase where you're stuck to the wall, the entanglement's an area law. If you're at the critical point, you had logarithmic entanglement. So this is nice because it's an explicit construction of a critical state, but you might say, you know, what's the big deal? The complexity of describing this thing as an MPS was algebraic. The size of the memory required here is also algebraic. Like, you know, you haven't really won relative to classical, you know, simulation of the state in an MPS or something like that. Okay. So what we'd like to do is we'd like to do better. We'd like to construct states that are more entangled than just logarithmically. And so, you know, can we do that? Well, of course we can, because otherwise it would be talking about something else. And so the way you do this is, again, following some old ideas of Peter Shaw's, where you say, okay, random walk isn't, you know, it only has logarithmic entanglement, but if you wanted to make it more entangled, what you would do is, instead of having a regular random walk, you have a random walk with colored steps. And so each up and down step in this random walk now is either, I guess you can't really see these colors, but it's either blue or red. Okay, and so a blue up step has to be matched to the blue down step, and likewise, yeah. No, the entanglement, when I talk about entanglement, I'm talking about the entanglement of the emitted state, right? So I'm talking about, so remember that so the emitted state looks, so I have a state that I'm emitting, and it consists of all of these qubits, and there's some virtual space. So at the end of this process, there are no 3 degrees of freedom in Alice's state, because I've measured Alice's state out into a rank 1 product state in the case where it's local. Like the random walk was local in the relevant sense. Right, so I'm talking about the entanglement of this state. I'm saying, let me take Bob's qubits and let me partition them into 2 buckets. Let me trace over 1 bucket, and like ask about the entropy of the density matrix, the other bucket. Okay. Right, so by going from the uncolored random walk to the colored random walk, where each up step has to be balanced by a down step the same color, You see this blue has got to be balanced by that blue, this red's got to be balanced by that red, and so on. By doing this, you can straightforwardly see that that the steady state of Bob's the state of Alice's system, that's described, that's governed by the stochastic process, now has extensive entropy in the height of this random walk, because there's not just where the random walk got to, but there's also a precise sequence of red and blue steps that has to be remembered in order to create the state. So you need a memory that has, in some sense, the ability to hold an extensive entropy. Yeah, Jonathan.
Are you assuming all the right steps?
I'm not assuming that yet. So that's going to be a thing. That's going to be a parameter, right? Just like in the uncolored case, I had a left step at some rate, a right step at some rate. Now I'm going to have left and right steps at some different rate. But I'm going to, for the purposes of what I'm going to talk about, it's not useful or important to make the blue and red rates different. So I can leave those the same because that's how I do best in terms of generating entropy. Okay, so now I play the same game. So I now have the same random walk, but now instead of just walking in and out, Alice's walker is something like a snail. As it moves out, it deposits a trail of ones and twos, which are red and blues. And as it walks back, it erases the trail that it had previously generated. And so this process allows me to both generate a ton of entropy and also wipe it out with some reasonable probability. So my post-selection is reasonably likely to succeed. And so now I have the same phase diagram. I have a phase in which the snail is stuck to the origin. I have a phase in which the snail wanders out to infinity. And I have a point in between where the snail is undergoing an unbiased random walk, depositing ones and twos as it goes. And so the upshot of all of this, oh yes, I can also just turn the crank again and write this out as a unitary dynamics on a chain. But now in order to do this, I need a little more complexity on the chain. I need a few more symbols because I need to make sure that I need to make sure that Alice's system is actually holding the memory of the random walk that happened up to this point. And so you can think about it sort of as like a tape, and there's a symbol that marks where the head of the tape is. And to the right of the head of the tape, it's all zeros. And to the left of the head, the tape contains the history of everything that's happened up to that point. And the tape can either, when a new qubit comes in from Bob, always in zero, the tape can move in one of many ways, which corresponds to the various possible transition rules various possible transitions that could have occurred. Okay. And so you might worry about whether this is local because it seems as if I have to keep track of where the head of the tape is. But the way you deal with this is you think about, for example, you can imagine that Alice's system is some kind of one-dimensional spin chain, and there's a waveguide or something else underneath it where qubits keep coming in from the left. They keep coming in and they keep trying to interact. They can't interact until they see the head. Then they interact with the head and they keep going. So it's Markovian because these guys are in a conveyor belt which keeps moving to the right. So they only interact with the system once when they touch the head. And it's local because these gates are strictly local on a two-leg ladder. And so this can be, so this is a local process. And the key point is that this process can create this highly entangled state, which has entanglement that goes as square root of system size because the random walk goes, to the square root of time in a time t. So this creates an algebraically entangled state, but the temporal overhead is also the 3/2. Whereas if you tried to prepare the state using adiabatic state preparation or something like that, it would be a substantially higher power of L, probably something like L cubed. so this process, at least for this concrete example, gives you a parametric win in terms of how easy it is to prepare the state. Okay, and so I'm nearly done, let me just say one more thing, which is that this example is a particularly simple instance of a much broader class of objects. And so if you've done any theoretical computer science, you'll recognize my tape-like construction as a push-down automaton. The key property of a push-down automaton is that it's got a last-in, first-out memory. So it can only see the last thing you popped on top of it, but it can hold a lot of memory. It can hold an unlimited amount of memory, but it can only access the thing that's all the way at the top. So now it turns out that matrix product states correspond to an even simpler class of machines called finite state machines. And so the Motzkin state and various other highly entangled states seem to belong to this sort of first non-trivial class of memories in computational devices. So that's so I don't have time to say more about that, but let me just point a couple of directions going forward from this. So the Motzkin state has entanglement that goes as square root of L because it corresponds to a diffusive. It corresponds to diffusive snail, but I can go back to a review article on anomalous diffusion, and it's very straightforward to make an anomalously diffusing snail. And if I do that, I can get entanglement that goes. I can get easily constructible states with entanglement patterns that go as L to 3/4 and so on. And so the more sort of general purpose message I want to convey is that there's an interesting relationship between phase transitions in open systems and phase transitions in families of quantum states. And by going to a non-equilibrium classical phase transition and turning this crank, you can come up, that gives you a recipe to come up with a number of new highly entangled states that might have interesting quantum information preserving properties and that haven't really been studied in detail. And so you can play the same game in higher dimensions where instead of a random walk, you have a surface growth problem, but the phenomenon is basically the same. Would be nice, and what hasn't been done so far is to think about the continuous time variant of this, because there's nothing fundamentally discrete time about what I was saying. It just turns out that it's much easier to conceptualize things and draw pictures when you're talking about circuits. And finally, this protocol where you emit qubits in some entangled state isn't a theorist's fantasy. This is how measurement-based quantum computation works. And so if you think about experiments or experimental platforms that are designed for measurement-based quantum computation, those are likely to be interesting places to explore other varieties of entangled states and things like that you could study this way. So that's pretty much all I had to say. So thanks for your attention.
Probably have time for a couple of questions. Yeah, one at the back. Motzkin volume law type state, it presumably could happen at a ground state of that spin chain, right?
Yeah.
So it's like seems to be very pathological to have a volume law ground state in this spin chain. So if you kind of project a local operator onto that state, the operator expectation value probably will give you signatures of a chaotic system.
It's not really chaotic because it's not scrambled. It's highly entangled, but it's entangled in a specific pattern that's not really a scrambled pattern. So if you look at things like the tripartite mutual information, they're very different between, say, the Motzkin state and a state you get out of a random circuit.
Yes.
But yeah, I mean, so you can ask if these are all ground states, and the answer is in general, no. So these examples with, say, L to 3/4, the super diffusive examples, I don't think can be realized as ground states of local Hamiltonians. The fact that Motzkin can be realized this way is actually a bit of a coincidence. Mm-hmm. But it's kind of interesting. I mean, it's nice because it allows you to say, this is in a case where adiabatic state preparation is an option, this beats adiabatic state preparation, but often that's not even an option.
Mhm. Okay.
Yep.
Thanks for the nice talk. So I wonder if you can do something similar for the Friedkin case,
Yeah, absolutely.
in which case instead of Q-treat, you can consider qubit, right?
Yeah, no, that's a good point. To get the really highly entangled Friedkin case, though, you need colored Friedkin, so you'd need spin 3 halves. So you go down from 5 states to 4 states. So in practice, that might be a really good idea anyway. But yeah, so there's entire family of interesting states like that we're beginning to explore. But yeah, Motzkin just happened to be the simplest place to start because it was the one that at least I was the most familiar with when I started thinking about this problem. But yeah, Friedkin is it's exactly the same. It's sort of yeah.
Thank you.
Yeah, so is there any structure to these entangled states, or are they, are they random kind of states? Or if you looked at concurrence between 2 spins, for example, would that have a large value?
They're very far from being random. So one thing you can see, for example, from this construction is that if you look at the mutual information in this colored walk state, there's actually a lot of mutual information because, if you have some unbalanced blues on one side, they had to come down on the other side somewhere. So mutual information has this like fairly long range structure, which is totally different from a random state, whereas the mutual information between any 2 small subsystems is essentially 0. So these are very non-random states. And I mean, in some sense, that's why they've got to be constructed by sequential circuits rather than just running a random quantum circuit out to time t goes to square root L.
Okay, I think we should wind it up there. Let's thank Sarang again.